To sketch graphs, we're going to combine together information from a few different sections, including monotonicity, concavity, what we know about asymptotes, limits, and other sources. Here are the steps. The first thing to do is to determine the domain. This is going to actually help understanding how big our sketch should be, what our asymptotes might look like when we get to that step. So we state what the domain is as our first step. Then we go and calculate both the first derivative and the second derivative. We're going to need that so that we know when the function's increasing and decreasing and when it's concave up and concave down. Once we have the first and second derivative, we're going to find all of the critical points and inflection points, which are known as transition points. Then we're going to find the asymptotes. Some of them we can look back to the domain. The vertical ones we can look back to the domain, but we'll also find the asymptotes if there are any horizontally. Then we're going to put all this information together to draw arcs. And there's a chart that will help with this, which I'll list in a second. And we may need to add additional information. The x and the y intercepts, for instance, are really helpful. Also helpful are to list out any zeros if we can calculate those fairly easily. So the transition points and drawing the arcs, there's a chart that will help you understand what the arcs will look like in different intervals of our graph, and the chart is as follows. Our chart's going to use the information from the first derivative and second derivative from concavity and from monotonicity to determine what the curves are going to look like, what the arcs are going to look like. So the first derivative could be positive, increasing, or it could be negative, which is decreasing, and the second derivative could be positive, which is concave up, or negative, which is concave down. So if we look at the pictures of concavity, concave up looks like this, and concave down like this. And if you cut these in half, you have areas where the slopes are increasing, and you have areas or zones where the slopes are decreasing. And we can fit that into our chart quite nicely. So if the graph is concave up and it is increasing, the arc has to look like this. If it is concave up but decreasing, the arc has to look like this. If it is concave down and increasing, the arc has to look like this. And concave down and decreasing, the arc has to look like this. Let's take a look at an example of how to put this together. Okay, in this example we're going to sketch f of x is equal to 1/3 x cubed plus x squared plus 3x. So we start off by noticing that the domain is all real numbers, and therefore there's no vertical asymptotes. So let's go ahead and take the first derivative and look for some critical points. We get x squared plus 2x plus 3, and we try and solve that for 0 or when it's undefined. And so does this factor. Two numbers that multiply to 3 that add up to 2. 3 and 1, nope. -3, -1, nope. So unfortunately this doesn't factor. We could go to the quadratic formula, and the most important part is to check the discriminant, because if that's less than 0 we don't have any solutions. So 2 squared is 4, minus 4 times 1 times 3, that's going to be negative. So this has no solutions, so there's no critical points. So now we can go take a look for inflection points. Calculating the second derivative, I get 2x plus 2, and setting that equal to 0 gives me x is negative 1, as the only inflection point. So when I make my intervals, I go from negative infinity to negative 1, and from negative 1 to infinity, and I check my first and my second derivative by finding values that are in those zones and plugging them in. So I pick a value less than negative 1, like negative 10, and see what the value of the first derivative is, in which case I get 100 minus 20, so I really only care that it's going to be positive. And if I check negative 10 in the second derivative, I see that it's negative. And then I pick a number like 0, so I continue to get positive, and 0 in the other one now gives me positive. So I can say, okay, well, this is concave down, but increasing, so it's this shape. And this is concave up and increasing, so this shape. And it switches those shapes when my x value is negative 1. So f of negative 1 is equal to 1/3 of negative 1 cubed plus negative 1 squared plus 3 times negative 1, which is equal to negative 2.3 repeating. And so now I can sketch my graph. Here's my axes, my y, and my x, and when x is negative 1, my y value is negative 2.3, and up to that point it has this shape, and past that point it has this shape. Now, if I want to know what the value is of the x intercept, I could make y equal to 0 and solve this, and it turns out it's 0. So it goes right through that point and up. And there's my sketch. In this case, our function is a trig function plus 1/2 x, and it's just defined on the interval 0 to 2 pi. So I already know my domain is xer, but it's from 0 to 2 pi. And I can calculate my first derivative, which is cosine x plus 1/2, and my second derivative, which is negative sine x. And I can calculate possible critical points, which is when it is, this is step 3, when it is equal to 0, and that happens when cos x is negative 1/2, and that happens when x is 2 pi over 3 or 4 pi over 3. Calculating when the second derivative is equal to 0 means solving sine x for 0, and that can happen when x is equal to 0, pi, or 2 pi. I put that together in a chart, knowing that there's no asymptotes for number 4. I can move on to drawing my arcs, and I now have a bunch of intervals that need to get tested in a chart. So let's build a chart and test some intervals. So my first interval is from 0 to 2 pi over 3, and then the next interval is from 2 pi over 3 to pi, and then pi to 4 pi over 3, and from 4 pi over 3 to 2 pi. And I've now included all the inflection points and all the critical points, and I can look to see what's happening on each of these intervals with the first derivative and with the second derivative. So picking points in each interval will allow me to know, am I dealing with concave up, concave down, and increasing and decreasing, and I can use the combination of those to tell you what the arcs are looking like in each interval. So let's calculate these, finding some points in each interval and substituting them in to the appropriate function equations that we've already calculated. The first and second derivative equations gives me positive and negative in these ways. Therefore, if it is concave down but increasing, it looks like this. Then concave down and decreasing looks like this. Concave up and decreasing looks like this. And concave up and decreasing looks like this. and concave up and increasing looks like this. So we can start to sketch this graph out, and I know that it is only defined from 0 to 2 pi, and I know that if I substitute in 0, it goes through 0, 0, and if I substitute in 2 pi, it ends up being quite high at 2 pi and over 3, at pi, at 4 pi over 3, I've got these transition points. 2 pi over 3 gives me a certain value. It's a critical point, so that's actually going to turn out to possibly be a local min or local max. Pi gives me a certain value. 4 pi over 3 gives me a certain value. And I know that from 0 to 2 pi it needs to look like this. And from 2 pi to pi it needs to look with this arc. Then it moves on to the next arc shape and the next arc shape. I can then see where I have a local max, I have a local min. This turns out to be my absolute max. Here's my absolute min, and you can see the concavity shifting at pi, which is the point where we saw switching from concave down to concave up. The questions in the pre-class assignments and other examples in the textbook will show you what happens with asymptotes and what happens as we increase the number of transition points. There's just a lot more zones to be tested. As you can imagine, a quartic function, a W-shaped function, has a lot of these transitions between concave up and concave down, and increasing and decreasing. When you add in asymptotes, the concavity can switch on each side of the asymptote. We need to take all of that into consideration when we're dealing with the intervals and then making our sketch. So I think you have enough pre-class knowledge now to try those questions, and we'll discuss them in class.